of the sarcomere are thin filaments. Does that make sense? To attach to the Z line and going towards the interior are thin filaments. Thin filaments. Okay. Attached to the M line and going towards the Z line are thick filaments. And so forth. Do you guys understand? So these are thick filaments. There's more I have to tell you. I just want to show you. You see, here's a Z line, here's a Z line, right here's the M line. Going from the Z line, going inward is thin filaments. Going from the M line, going outward is the thick filament. Okay. Now, the area where you only find do you see the area where you only find thick filaments? Right? Area where you only find thick filaments is called the H zone. H for house. H zone. H zone. H for house. The area where you only find thin filament is called the I band. I is alone, right? The area where you only find thin filaments is called the I band. The area where you see the thick and thin filaments are overlapping, okay, it's called the A band. A for apple, A band. Area where thick and thin filaments are overlapping is called the A band. Now right now, the thick and thin filaments are not interacting with each other, okay? They're separate. When they interact, that's when you have contraction. Now, what holds the thick filaments attached to the Z line? So there's another protein that is another protein which holds, that attaches the thick filaments to the Z line. It's called tintin. Tintin is a protein that attaches the thick filaments to the Z line. Tin, tintin.
I'm sorry, one more time you said it does what?
It attaches the thick filaments to the Z line. It attaches the thick filaments to the Z line. Because thin filaments are directly attached, right? But how are thick filaments attached to the Z line? Via a protein called tintin. Make sense? You guys understand this?
Can you repeat that again? I'm sorry. The tintin attaches
The thick filaments to the Z line. So sarcomere, basically some characteristics of it. 1,000 in one myofibril arranged end to end. Shorting of all sarcomeres at once causes the muscle cell to contract and in turn to hold the entire muscle to contract. Contains two types of filaments, thin filaments and thick filaments. Now, what is the thin filaments made up of? Actin chains plus TTC. We'll talk about what TTC is or actin chains a little bit later. But right now, contains thin filaments, which are actin chains and TTC plus TTC. What is thick filaments made up of? Myosin molecules. Now, all of these are proteins. Composition is a protein. TTC are proteins, actin is a protein, molecules are proteins. Muscle contraction is dependent on the interaction between these two filaments. Actin chains and TTC, and then myosin molecules. So right here, you could see the Z line, M line, this area where you only find thick filaments is H zone. I band is where you only find thin filaments, and this one is where you find the interaction overlapping. Now let's talk about more detail about thin filaments. Where do you find thin filaments? What is the location of a thin filament? It's attached to it. Is it found within a Z line? No. So you could say I band, A band, but what structure? Sarcomere. Within the myofibril, right? Because sarcomeres is found within a myofibril, correct? Yes? You guys understand that? So it's found within a myofibril, sarcomere. Depends what choices I give you, right? If I give you a sarcomere, if I give you something else. So myofibril is a correct answer. Sarcomere is a correct answer. Depends what choices I give you, right? So, but it's directly located within the sarcomere. Sarcomeres are found within the myofibril. What is the function of thin filaments? Contraction, allows contraction to occur. Now, in here, you need to do some correction. So cancel this part. Just say actin chain. Okay? Plus TTC. I haven't gotten around to change my notes. So composition of thin filament, actin chains plus TTC. Now in this slide, we're just going to focus on actin. I have another slide for TTC, which we'll talk about a bit later. So let's just talk about actin. What is actin chains made up of? Two chains which are made up of actin molecules. Does that make sense? So actin chains are two chains, and each chain is made up of actin molecule. Now, actin molecule, so let's look at what actin molecule looks like. Actin molecule looks like this. This is what one actin molecule looks like. Okay? Here's the actin molecule, and the actin molecule right here where I drew it black, it's a myosin binding site. Actin molecule, actin is a protein, it's a globular protein, it's like a round protein. Okay? Each actin molecule has myosin binding site. Does that make sense? What is a pearl chain made up of? What is a pearl chain made up of? Pearls. Okay? Imagine that pearl chain as an actin chain. Okay? Each pearl is actin molecule. Isn't it round, globular? So actin looks like that round. Okay. Now, do you see the, if you imagine a pearl chain, the site where the chain, the string could actually go through, doesn't it actually have a little hole? So imagine that hole is myosin binding site. Does that make sense? Okay, imagine a chain. And doesn't a chain actually have two sides? If I hold it up, there's one right here, one right there, right? A necklace or a pearl necklace. So doesn't it have two? So that's how it would be. Here's one actin chain, here's another actin chain. Okay? That's what actin chains look like. Yes?
So they're going to have two myosin binding sites?
Yes, one at top, one at the bottom. I mean, each molecule only has one, but because you have two chains, so one up here, one up here. Does that make sense? So usually what does actin chains look like? So you have multiple, I should have color coordinated. Colors are kind of reversed. Okay? So that's one chain, and you would have another chain coming down here. So here is each of these actin molecules. Here's a myosin binding site. Right here, you have the second chain. They also have a myosin binding site. Does that make sense? Okay? Now, I can't keep on drawing it like this, okay? So what I do is I tend to draw it this way. So each, there's one actin molecule, second actin molecule, third actin molecule. I draw it like these, two actin chains, okay? And then I draw the myosin binding sites. So this is how, from now on, because I can't seem to do it this way, I can't explain this stuff. So this is how I will tend to draw actin chains with the myosin binding sites. Okay? Make sense? Can I go on to the next slide? Yeah. So forget right now, forget D at the moment, forget B, forget E. I haven't taught you that. Only thing you need to see right now is basically A and C. Do you see each of this is a actin molecule? Do you see that it forms chains? So you have two chains. Right here, you see are myosin binding sites. So A is actin molecules or actin chains. C is myosin binding sites on each actin molecule. Does that make sense? We'll talk about B, D, and E a little later. So this is what a part of thin filaments look like. Entirely this is thin filament. It also has a TTC in here, which that's why I crossed it out. I haven't explained the TTC of it. Okay. Now, before we get to TTC, let's kind of talk about thick filaments. Now, where do you find thick filaments? Location of thickness, sarcomere, sarcoplasmic, sarcomere. Yes, yes, sarcomere. And sarcomere is found within a myofibrilla, right? Which line is it attached to? M line. Under what band is it found? A band and H cell. Function of thick filaments, again, allow muscle contraction to occur. Function. Oh, allow contraction to occur. When thick and thin filaments interact with one another, you will have contraction. Now, what is a composition? Composition of thick filament is multiple myosin molecules put together. Composition is multiple myosin molecules put together. Multiple myosin molecules put together. That's a composition. Now let's look at the structure of myosin, and then we will look at the structure of the thick filaments. Myosin is a protein. This is what the protein looks like. It has a tail. This is one myosin molecule. It has a tail and it has two heads. One of the head is has an ATP bound to it. Right here is the ATP binding site. Okay, at certain times it has an ATP bound there. Certain times it does not have an ATP bound there. So when it does, it's like ATP is bound there. When it doesn't, it has an ATP binding site, right? Now, the second head. So both of these are heads. So here's a tail, two heads. One of the head, it has an ATP binding site. The second head is the head that actually binds to actin. Remember, actin has myosin binding site. So what part of myosin actually went and attached there? It was the second head. Does that make sense? Yes? Okay. So this head allows ATP to bind there. This head actually binds to actin. One head binds to actin, the second head binds ATP. Okay? Makes sense? Now, what did I say? That thick filaments are multiple myosin molecules put together. So this is what thick filaments look like. Now, I can't draw two heads, so I just draw a dashed line. But that should represent it has two heads. I'm not an artist, okay? So that dashed line should indicate that there are two heads. well, I can't seem to draw it at the bottom, but it also has ATP bound. Does that make sense? So basically, this is what thick filaments look like. All of the tails are right in the middle, but protruding outward are the heads. And one of the head has ATP bound to it, which it would have it right here too. I just can't seem to draw it down there. But, and the second head is open to bind to actin. Okay? It looks like a golf club, where it has a stake and then the head. Okay. So right here you see all of the tails. Okay? Protruded out, you could see the heads. As you can see, each one has two heads. One of the head is ATP binding site. The second head binds actin. Okay? So the tails, the two heads, one of the head will bind ATP, another head will bind actin.
Does it really matter which one is the binding or which one?
In reality, yes. For this class or even for physio, you don't need to know that. That's more if you go into PhD or when you're trying to do drug stuff. Okay. Make sense? Any questions so far? So A is just showing you the heads. C is just showing you the tails. The head and the tails together make up the myosin molecule, or the thick filaments. You can see it has two heads. One of the head is an ATP binding site, while the second head is actin binding site. Make sense? Easy enough so far? Okay, now let's look at the TTC. So TTC stands for troponin tropomyosin complex. TTC, troponin tropomyosin complex. Now, composition. TTC complex, troponin and tropomyosin are both proteins. Two different proteins which are attached together. Okay? They're found attached together. And that's why it's called a complex. Troponin tropomyosin complex. Now let's just look at the structure of tropomyosin. Tropomyosin is a protein, but it more looks like a fiber, like a thread or a rope. Okay? So it's a protein that just looks like a filament. Okay? It structurally, it looks like a fiber, long fiber, like a long cord or a rope. Troponin is a globular protein which has three different segments. Three segments. This segment is called the TT. This is called the TI. This is called the TC component. The T, so this part, this. This T stands for tropomyosin. This I stands for interaction. The C stands for calcium. Okay. So troponin, tropomyosin, troponin interaction, troponin calcium. Okay? The first T stands